Hello everyone.
Good morning.
Good morning.
Nice. Okay, so we do have a few people. I think 6 of you. We'll just wait one more minute. So already this guy, if you are present, you can go to the website, which yesterday I think Mr. Zions provided you with, UPEL, and please just tick that you are present on these classes. It is in IR spectroscopy folder. I think it will be already 10 o'clock in a few seconds, so you will be able just to mark that you are present on the classes. All right, we do have 8 people. All right, it's 10 o'clock, so maybe I will start. My name is Maciej Bik, and it's my great pleasure to run classes with you from advanced research methods and concerning IR spectroscopy, so infrared spectroscopy and scanning electron microscopy. And maybe I will, in the beginning, I will show you my, let's say, share my screen. And I would like to have your feedback. Do you see it?
Yes.
We can.
Okay,
Yes.
perfect. So maybe in the beginning I will check, let's say, an attendance list, and maybe we'll see who is absent. So maybe I will have my list here and I will read it loudly, and you will just show me yourself for a short time. So, Mr. Marceli Hryniewiecki. No problem, no problem. Miss Susanna Cantor.
I'm also present, but I also have problems with camera.
Okay, okay, that is not a problem. Miss Eva Kozub.
I'm present, and I also don't have camera here in my remote computer.
Okay, so let's assume.
So sorry for that.
No, not a problem. So maybe we will change the plans. No one has to show me yourself. There is not a problem. I hope we will see each other during laboratory classes. So Miss Claudia Wyszczarz. Is she present?
I guess she has problem with her network.
Okay, okay, I see her, but okay, maybe she will solve it. Miss Sylvia Manteris.
Manteris, present.
Manteris, yes, okay, thank you. Miss Małgorzata Mendela.
I'm present.
Thank you. Miss Agnieszka Mojecka.
Hi, I'm present.
Okay. Mr. Tomasz Myćka.
I am present.
Okay. Mr. Artur Polaczek. Is there any feedback? Do you know that he will be absent today? Right, so yeah, but he signed himself on the UPEL, but I cannot see. Maybe he has some problems with internet. Mr. Patrick Zając.
Yes, I am.
Thank you. And Mr. Jakub Zaid.
He's not studying with us. He's studying functional materials, but in Polish language.
Okay, all right. And is there anyone that I didn't read? And I should?
Me.
Okay.
Kalowski.
Talowski Patrick, and I would like to ask a question.
Yes.
Where should I sign in the UPL?
Well, there is a fold. I think you should sign yourself for these classes, but maybe I see that you are present here, and I think it will take too long time right now to let's say maybe you can ask your colleagues after classes, let's say how you can sign yourself to the course, because I cannot see you. And yeah, I see that you are present, so I think that's enough for now.
Okay, no problem.
It's me, Marcin Tomkiewicz. I'm
okay. All right.
And I'm also not on UPAL, so.
All right. So you will I ask you that after classes you will ask your colleagues to let's say they will help you to sign for the course on the UPEL. All right, so we do have right now 12 people. Okay, so
yes, hello, I'm sorry for being late.
Okay, Mr. Arthur is present. All right, so we do have 12 people. You are present. You told me you're present, so you will be paying attention. It's nice. Okay, and right now I will start with the presentation. So first, today we had an introduction to the vibrational spectroscopy in middle infrared range, and some information about me, about the classes. But before, if there is anything that you would like to, let's say, tell that there is something wrong with the presentation, or you don't, let's say, you don't see something, or something is too fast, or whatsoever, so then just please tell me. And just please tell me, and I will go back, I will repeat, and I will answer a question. So as I told you before, my name is Maciej Bik, and here you have my email address. You can find me in room 312 in B8 room, in B8 building. And about consultation hours, basically right now in the COVID time, I prefer the email, and you can write me email whenever you want, and we can discuss whatever you would like to discuss. I'm checking my email, let's say 10 times a day, so I think you will get an answer really quickly. But if you would like to come to the laboratory, repeat something and make some measurements, also there is not a problem, but right now you will have to get some approval that you can go, say, be in the laboratory. So about the classes themselves, so conditions to pass ER spectroscopy and SEM. First of all, you have to be present. You are present. I'm happy with that. You have, let's say, I think that you should be active during, let's say, lectures and lab classes. So there are no stupid questions. So you can ask me whatever you want, and if I wouldn't know something, I will check it and I will give you an answer during the next classes. This is also some kind of learning for me. Using English as much as possible. So this is what I already told some colleagues of you from Functional Materials group, because this is, I think, one of the most important part during these classes. I'm talking based on my own experience. So talking in English, and I will use some Polish words, Polish equivalents during these classes, just, let's say, to make it clear what I want to say. If there are some specific terms, let's say like uncertainty law of Heisenberg, so like zasada nieoznaczności Heisenberga, just to make it clear what I want to say. But if you are writing email, if you are asking something, so then I really recommend to use English in these official forms, because it really helps in the future. So the most important condition to pass these classes is to provide me with final report, either from ER classes plus SEM, or SEM for those, I think, 3. There will be 3 people who can, let's say, omit infrared spectroscopy classes because they already passed these classes in let's say, during bachelor studies. So, and really important part, that in this really big email, big information, let's say, before these classes, I asked you to choose substances for this whole course and to divide yourself into subgroups of 2 people. So I would like to have a feedback in the form of email. Let's say you can prepare some kind of table for me that there will be this division with subgroups of 2 people and what kind of substances you would like to measure and what is the form of the substance. Is it powder? Is it bulk material? Is it, let's say, I don't know, some kind of dried small animal or whatever? But you have to remember it has to be dry. It cannot be liquid. It cannot be wet because you cannot put it into the SEM microscope. And let's say final test, which will cover all topics, let's say not only SEM, IR, but also XRD, thermal analysis. It will be, I think, in the end. And guess who is preparing questions concerning this part? So I am preparing questions, so I recommend to pay attention to these lectures and to the lab classes. And I was also a student, so I really like giving good grades. And you have to pay attention to some special signs during lectures because it may help you to pass the final tests more efficient, and then you will have better grades. All right, so the current schedule for the laboratories and lectures, let's say it assumes that we should have 1 lecture from vibrational spectroscopy and 4 laboratories for 1.5 hours, which should be in April, and 3 lectures from SEM and 2 laboratories from SEM, which should be held in April and May. For now, everything has to be held online till 11th of April, and maybe later on, if we take into account our experience from last year, it took much longer, and let's say these online classes were, I think, till the end of the May or even like June. So maybe this time it will be sooner that you will be able to have those hybrid classes, and I really hope. So my idea is to change this plan a little bit because I see no reason in having 3 lectures from SEM with you and these 4 laboratories from IR, and my plan is to change it for, let's say, today we have this 1 lecture from infrared spectroscopy, but we can have 2 hybrid laboratories with 2 people each for around 3 to 4 hours after, let's say, lockdown, so probably or in May or sooner. It will be made within 1 Friday. So 5 people will come from 8 to 12, and another 5 or 4 will be present from 12 to 16. Because as far as I know, you have 3 Fridays. If not, if someone is working, if someone has some, let's say, extra classes or whatever, so-called obieraki, so some extra classes, they are sometimes on Friday. So we can have 2 groups. 1 group will be on Friday, a second group will be on any other day, let's say, date that it will be good for you. I'm really flexible and there is not a problem. The most important part for me is that every person will measure at least 1 substance, prepare so-called 1 pellet, and make post-processing using Opus software. In total, it will take 3 to 4 hours in 1 day, let's say on Friday, but at least you will see the equipment, you will touch it, you will feel it, how does it work, because I really see no sense in showing you that online. If there will be such chance, I think we should take it. We should meet on some day and we should, let's say, I think it will take maximum 4 hours that you will prepare the pellet. I will give you a short introduction, short repetition from the lecture. You will see the equipment, you will prepare your pellets, you will measure it, and then we will take our results, go down to the classroom, to the computer classroom, and you will post-process your results and you will prepare nearly everything. and afterwards we can have SEM classes. So then I think one lecture for 1.5 or 2 hours maximum is enough, that I will cover scanning electron microscopy, transmission electron microscopy, and energy dispersive spectroscopy. So these 3 techniques, 3 methods, and it is to decide. We can decide whenever it is good for you that we can have this lecture. I think it will be the best to have it before the laboratories, which I would like to also have one laboratory for 6 hours in total. And also after lockdown, made within another one Friday from 8 to 16, and every person will have a chance to measure one substance. Excuse me. To measure one substance for around 40 minutes using SEM and EDS. So it means that in total we'll have 6 hours, but we will have, let's say, like 10 to 12 people in total. So, but at least every person will take substance, glue it to the special tape, put it into microscope with his or her own hands and measure it. Take some pictures, some SEM images, make EDS analysis, so investigate the elemental composition by yourself. You will have a chance just to sit, to click, to make images using different detectors, and it is my idea, because also I see no sense in showing you everything online and you will be just sitting for 6 hours or I don't know, like 4 hours, and I will show you how I'm taking SEM pictures. So at least every one of you will have a chance around 40-45 minutes of taking pictures, making EDS analysis of your powders, bulk materials or whatever. And in the end, you will prepare a really nice report about structure of your material, so infrared spectroscopy, and microstructure, so SEM images. You will show me what kind of bonds are in the structure of your material and how does it look like under the microscope and what is the elemental composition, because you will have a chance to use the EDS method. So this is my idea, this is my proposal. Please think over it through during the Easter time, and the biggest advantage is that you will have some experience, that you will be in laboratory. And everything will be, let's say, held in with COVID constraints. So you have to wear, let's say, gloves, you have to wear masks. I will disinfect everything, let's say, like chairs and tables and whatsoever. But I hope that we can have these classes in such way, in such manner that you will be present in the laboratory. So please decide during Easter time, because let's say if you don't agree, if you will have some problems with that, then I have to prepare something, let's say, online. But I really hope that you will agree for that if they take the lockdown, so maybe in May or sooner, then we'll just, let's say, have a quick call and we will have one, or let's say these 2 Fridays or some 2 days, and your classes with me will be over. So we can make it really compact, really quick, but also really efficient. So let's go through to today's topic. So infrared spectroscopy. So first of all, I would like to tell what is basically spectroscopy. So something about electromagnetic radiation and investigated substances. What is actually the Fourier transformed infrared spectrum and what kind of values we will be describing, what you will use during preparation of your report. What is the beam route? Why do we have to use Fourier transformation? Afterwards, some let's say information concerning the pellet technique and potassium bromide as a reference material during laboratory classes, and in the end, really short comparison of infrared spectroscopy and Raman spectroscopy. And please just tell me, I have one more question. Do you also see this, let's say, all icons below here, or do you see full presentation?
Yes,
We can see our taskbar.
We see icons.
All right, and do you mind if I ask, do you have any idea how can I, let's say...
You probably need to read the message that you get on Teams.
Okay, read the message. Okay. All right, perfect. Thank you for your help. All right, so what is spectroscopy? So my favorite definition is that this is the field of science which describes how electromagnetic radiation wave interacts with matter. And I would like to discuss more these two things. So first of all, electromagnetic radiation, and second of all, in substances, materials that we can investigate with this technique, because this is the most important information that you should have after these classes. So in case of electromagnetic radiation, let's say the most crucial, the most relevant formulas or let's say laws that we will be dealing with is internal energy change according to the principle of energy conservation. Zasada zachowania energii. And here below you can see the equation, the Planck's equation for the change of the energy equal to Planck constant multiplied by the frequency, and frequency is equal to the speed light divided by wavelength. And those three, let's say those or two equations will cover nearly all so-called qualitative features of electromagnetic radiation wave. So parameters that are describing this, let's say, infrared radiation wave that we will be using. So we have change of the energy, so the delta E, we have frequency in hertz, and we have wavelength given either in nanometers or micrometers, apart from our constants, which is Planck constant and the speed of light. So these are the three most important qualitative features of the electromagnetic radiation wave that we can describe our wave, which let's say our material is subjected to. And there is also another, the fourth feature. We will discuss it in a few seconds. So what kind of energy, let's say, we can discuss in case of materials, in case of molecules, in case of atoms? So on the right side, you see a really nice scheme of quantified internal energy levels. And let's say we can differentiate these energies into translational, so the movement of particles, rotational, so just it is connected with the rotational movements. The most important for us, oscillation, so the movement around their equilibrium position, energy of electrons, and nuclear energy. And on the right side, you could see that those energy have different levels. So the highest is the nuclear energy, and the lowest is, let's say, transitional energy. And oscillation is in between. And this, we will go back to this scheme because we will discuss something like transferring of atoms or molecules between different energetic levels. And why I show you this diagram and why I discuss such different type of energies, because we will discuss only the oscillation energy, oscillation movement of the atoms, and that is why sometimes this vibrational spectroscopy is called oscillation spectroscopy. So in Polish, spektroskopia oscylacyjna, because we are dealing with the oscillation of atoms, oscillation of molecules. And what is basically oscillation? If you consider atom in a zero position, and then if it goes around this equilibrium position, let's say to the position X, it goes back to position 0, and it goes to the position minus X, back again to 0, X, 0, minus X. So it is oscillating. It is not moving to the position X and staying. It is not rotating, but it is just oscillating, so moving around the equilibrium position. And I think it is obvious for me that you heard something about gamma radiation, X-ray radiation. You already, I think, you passed X-ray classes, UV rays, visible light or microwaves, and infrared. So these are all different types of electromagnetic radiation, let's say, taking into account or differentiated by a wavelength. So you see here on the graph that infrared is within around 760 nanometers till 1000 micrometers, so till 1 millimeter. And the infrared region can be divided into 3 regions: near infrared till 2.5 micrometers, the medium or middle infrared, which is most important for us, between 2.5 and 25 microns, and far infrared till 1000 microns. And on the right side, you could see an equation for the 4th qualitative parameter, which we are describing the electromagnetic radiation. It is a wave number, and you could see that it is nothing new. It doesn't, let's say, it isn't taken from any specific law. It is just the 1 divided by wavelength. So it is, let's say, really simple, but in 99% of literature works or any publications or books nowadays we are using this parameter to describe electromagnetic radiation wave in case of infrared spectroscopy. So below in the table you could see parameters such as wavelength and wave number for these 3 different regions of infrared radiation. Near infrared, in Polish called bliska podczerwień, middle infrared, środkowa podczerwień, far infrared, daleka podczerwień. And most important for us, middle infrared, wavelength between 2.5 and 25 microns, which means that we are using different, let's say, some range. So what does it mean? It means our radiation is polychromatic. It is not monochromatic, because then we would have to use only 1 wavelength, but it is polychromatic, and the region of wave number from 4000 to 400 reciprocal centimeters. It is important to remember that reciprocal centimeter is the unit of the wave number, because before, a few slides back, I told you that wavelength is given in nanometers or micrometers, but somehow we are using wave numbers in reciprocal centimeters. And here, just to clarify, to repeat, another 2 formulas for the Planck's equation and equation for the frequency. So all those 3 equations in total cover our 4 qualitative features of the electromagnetic radiation wave. And how the radiation can interact with the matter. So first of all, you could see that there are some different types of emission. So the radiation can be, let's say, the sample can be exposed to radiation, and due to this interaction, some either positive ions can be emitted, and it is used during the mass spectrometry, or some photoelectrons, some electrons can be emitted, and then if we are using XPS, so X-ray photoelectron spectroscopy, we can use this interaction. Another kind of interaction is scattering, so from Polish rozpraszanie. So scattering is a really important physical phenomenon used, or it is fundamental base of Raman spectroscopy, another really crucial method from oscillation spectroscopy. So scattering is like absorption and spontaneous, really quick emission. So the material is absorbing energy, but it in, let's say, 10 to minus 14 seconds, so really quick, really spontaneous, it is emitting this energy. And the most important for us, it is absorption. So if the material is absorbing energy. It is taking this energy from, let's say, from the source, and is not giving it back. So something has to happen that we will discuss it in a few slides. And next to absorption, you see the term transmission. These two terms are, let's say, they are used together, or they are used either transmission or absorption. Because if material is not absorbing energy, it's transmitting the energy. So not only infrared spectroscopy can use this physical phenomenon, but also UV spectroscopy or NMR techniques, or nuclear magnetic resonance. But for us, the most important is infrared spectroscopy. So the most important thing, how we can differentiate the interaction based on type and energy of interaction. So type, we already told, emission, scattering, or absorption. And energy of interaction, so depending what type, let's say, what kind of wave, or which range of wavelength, which type of electromagnetic radiation we are using, energy of interaction will be different. And if we already discussed investigated substances, what we can measure, let's say, sorry, electromagnetic radiation. So what are the qualitative features describing this radiation? So right now we have to, let's say, discuss what we can measure. So spectroscopists are interested in investigation, in evaluation of material structure, of material, what kind of bonds are present in the material. And they see one specific bond, let's say between two atoms, as a system of masses connected elastically. And many times we give an example of spring, that our bond is like a spring which connects two atoms that you can see on the graph on the right side. So let's consider our bond as a spring, and that is why it is called oscillator. Because if, let's say, spring, if you, let's say, change its length, if you spread it, then it goes back to its equilibrium position. So it's like it makes oscillation movements. So it goes back to some x position, 0, x, 0. So that is why we are telling about oscillator. We treat our bond like an oscillator, and we are, let's say, spectroscopists are using either anharmonic or harmonic approximation. Why anharmonic or harmonic? Harmonic is an ideal case in which the material is oscillating with the same frequency all the time. And anharmonic is describing the, let's say, living world, the actual case, that this harmonic never happens. So let's say it's more like anharmonic oscillator is describing our real world, how everything looks like, that the energy difference between energetic levels are different between 0 and 1, first and second, second and third, which you see on the graph with the blue graph and the green graph. So the harmonic, let's say, oscillator is more often used just to describe processes, just to describe every law concerning infrared spectroscopy. So it is just approximation used to describe the technique, and anharmonic approximation used to describe the real world. So vibrations, so the movements of the atom, are dependent on bond energy. So this is the first feature, expressed in the form of force constant, expressed in F letter. So the higher force constant is, the higher is the bond energy. So we can say simply that the bond is stronger, that some bond is, let's say, like silicon carbon and silicon oxygen. Let's consider these two bonds between silicon oxygen and silicon carbon. So one of these will have higher force constant, like silicon carbon, and it will be much, let's say, it will be slightly stronger than in case of silicon oxygen bond. And the second parameter, if I told you carbon and oxygen, so you know that the masses of these atoms are different. So this will be also a second parameter that is really influencing the vibrations of these molecules, of these bonds. So we are not directly using the masses of the atoms, but so-called reduced mass, which is just equal to the masses multiplied by themselves divided by their sum. And very important equation which connects both parts, our radiation and our investigated substances. So on the left side you see frequency, so one of the qualitative features describing radiation, and on the right side you see some mathematical constant, 1 divided by 2p multiplied by square of force constant divided by reduced mass. And it is a really important equation which connects both parts. And you see right now how we will be working, that the frequency of the vibration of the atoms, of the molecules, are dependent how strong is the bond and what are the masses of the atoms. And this equation tells us what is the natural vibrations of, let's say, frequency, częstotliwość drgań własnych. And right now we will discuss what are those natural vibrations. So just a few definitions. One of them, let's say, it is the most boring slide during this presentation, but we have to cover it, and you see a special sign, so it is also important in case of some final test or something. The absorption of infrared radiation results in changes of oscillation energy and can occur only when the infrared radiation frequency overlaps with internal vibration frequency of atoms or molecules. It's like bubbling. It's, let's say, I'm reading it and it's like bubbling. What does it mean? It means, or it tells you, why we are using middle infrared range or just infrared range. Because you can ask me, why infrared? Why not, let's say, X-ray? Or why not gamma? Why not microwaves? Because of the fact that let's say, internal vibrations of atoms, of molecules, of most of these atoms, of most of these molecules, so like around 90–95% of substances have internal vibrations. What does it mean? Interior movements. So vibration which cause neither movement of molecules mass center, so translation, nor its circulation, so rotation. We are not taking into account translation or rotation, only oscillation. So it means that 90%, around 90% of substances that we are trying to investigate have their internal vibration, so oscillation, have the frequency in the region of infrared radiation. And here you see overlaps. So it is in the same region. That is why we are using infrared region, because the frequency of the internal vibration are in the same region as infrared radiation frequency. And it is the, let's say, it is the clue, it is the most important thing from these two first points. The third point tells us what is the fundamental base of the infrared analysis, is the fact that molecules exhibit, every molecule exhibit particular specific characteristic vibration, so-called normal vibration, which can be attributed to specific bonds or functional groups. And it is quite, let's say, intuitive, quite easy, because on the previous slide I told you that vibrations are dependent on masses and on bond energy. That is why we can say that every molecule, every atoms, every 2, 3, 4 atoms connected by some bonds, they exhibit particular characteristic vibrations because they have their own masses and bond energies. That is why they can be attributed to specific bonds or functional groups, because we don't have to take into account only 2 atom system like silicon-carbon, silicon-oxygen, single bonded, double bonded, triple bonded, whatever. We can take into account vibration of whole functional groups, let's say like carboxyl group, COOH, or let's say methyl group, CH3. So not only 2 atoms, but multiple atom system. And what are what are those normal vibrations or those characteristic vibrations? So simultaneous movements of all molecules, atomic cores. This is really crucial here, that molecules, atomic cores happening in phase and with the same frequency. So it is, let's say, the most relevant part differentiating this technique from Raman spectroscopy. Because in Raman spectroscopy, we are more dealing with the valence electrons, the movement of valence electrons, so the outer part of the molecules. But here we are dealing in simultaneous movement of all molecules' atomic cores. Okay, and right now table and some equations to repeat. I told you, using these three equations, we can describe four qualitative parameters, and that vibrations are dependent on atoms' masses and bond energy. So let's see how does it work in reality. On the left side in the table, you could see different types of bonds of carbon with hydrogen, deuter, or another atom of carbon. So we see that going down from hydrogen, deuter, carbon, the mass of the second atom is increasing. So the reduced mass in our natural vibration frequency equation at the top will be higher. So in the end, frequency will be lower. And let's see in the table, we see the dependence of frequency. We see 420, 420, and 350. So the frequency is decreasing with increasing mass of the atom. So everything is correct. Also, on the right side, you see dependence of the wave number. So once again, for carbon hydrogen, we see 3000 reciprocal centimeters. Carbon deuter, 2100. Carbon carbon single bonded, 1200. And why it is important? Because having the knowledge, it works for both sides. First of all, if we know what types, let's say, what type of bonds are within our structure, or we expect some bonds, then we can, let's say, assume, we can expect in which region the vibration will occur. And from the second side, more important for us, if we see the result that the vibration occurs at a specific wave number, then we can expect a specific bonds present in the system. And dependence of frequency on the bond energy. It works also in the same. Carbon-carbon bonds are single bonded, double bonded, and triple bonded. So what does it mean? It means that with the increasing number of these bonds, the bond energy increases, so the F constant will be higher. So in the end, frequency in the equation at the top will be higher. And once again, we see that the frequency is increasing with increasing force constant. And some information at the bottom that frequency increases according to the relation that stretching higher than bending, higher than wagging or twisting. And what are those terms? Stretching, bending, wagging or twisting. These are types of normal vibrations. First of all, we can let's say differentiate stretching vibrations, sometimes called valence vibrations, which take into account change in the bond length. And we have either symmetric vibration, stretching vibration, or asymmetric stretching vibration on the right side. And I think you see that if we draw the line through the middle, the symmetry line, so on the left side we see a symmetric movement, on the right side asymmetric movement against this let's say imaginable symmetry line. And here I think you have a clue what kind of molecule it is. It is a water. So we have the yellowish atom of oxygen and two bluish atoms of hydrogen, and also two free pairs of electrons around the atom of oxygen. So stretching symmetric and asymmetric vibrations. And the second type of vibrations which are bending. So in Polish, stretching is rozciągające, bending zginające. So bending vibrations, sometimes called deformational, which take into account not bond length, but change in the angle between bonds. So first of all, we can have in-plane bending vibrations. So in Polish, drgania w płaszczyźnie, so scissoring, or out of plane, wagging, in plane, rocking, or out of plane, twisting. So 4 types of bending vibrations: scissoring, wagging, rocking, or twisting. And as you see, every one of them has attributed some Greek letter. So stretching vibrations is a letter Ni. It is not V, but it is a Ni letter. For scissoring, delta, wagging, omega, twisting, theta, and for rocking, rho. So all these Greek letters are attributed to the specific vibrations.
Sorry, can I have a question?
Yes, absolutely.
Because you said on the slide it's written in plane and out of plane.
Yes.
And isn't it mixed? I mean, isn't rocking and twisting out of plane and wagging and scissoring in plane? Or how are
yes,
they?
yes. You are correct. You are correct. So this is, yeah, maybe in plane, out of plane should be written in a different manner. So thank you for the comment.
Thank you.
Yeah. So see, yes. Important definition, important term: degrees of oscillation freedom in 8-atom system. Stopnie swobody oscylacyjnej. What does it mean? It means how much, let's say, how many types of movements are allowed in our system. And why do we see, or why do we use these 2 types of equations, like 3n-6 or 3n-5? N, it means n-atom system, how many atoms we do have in our system. Why 3? Because we have, let's say, movement of atoms or molecules in 3 directions, x, y, z. And y minus 6, y minus 5? Because, as you already know, we do not take into account translations and rotations. So minus 3 translations in 3 directions and minus 3 rotations. In case of minus 5, we consider linear molecule, so we have 1 additional direction, because it is linear. So 3n-6 and 3n-5. And the slide, which is the key slide in the presentation, because we will be dealing with rules of choice in infrared spectroscopy, from Polish, reguły wyboru. These are rules which tell us why or when the absorption, so the physical phenomena, which is the basis of infrared spectroscopy, may occur. So first of all, the first rule, which was already discussed: photons of incident IR radiation must possess the energy equal to the oscillation energy difference of energetic levels. And my face in the beginning looked like this when I read it for the first time. But then, let's say I read more, and I really like this expression, which I already described to you. It means that it just describes why we are using infrared spectroscopy. Because of the fact that internal vibrations, so oscillations of the atoms of the molecules, have frequency within the frequency of infrared radiation. And before, you saw, right now you know everything, and you saw the equation for the Planck's equation, that change of the energy is equal to Planck constant times frequency. So it means that if our molecule, our atom, wants or can absorb this portion of energy called quant, So the difference between energetic levels has to be exactly at the level of the energy of this quant. So please let me go back. Let me go back to this diagram. On the right side, you see the scheme of quantified internal energy levels. And as we discussed, we are interested in oscillation. So please have a look at the oscillation which is in here. And we see 0 level, first level, so the difference of the energy is 10 to minus 20 joules. Then we have first and second, second and third. So what does it mean? It means that if the absorption occurs, atoms which are on the 0 level, they are transferred to the first level. But this transition may occur only when atoms absorb the quant of energy, so the portion of energy which is equal to this difference. It cannot be equal to 1.5, to 2.5 or 0.4, because there are no such levels between 0 and first, between first and second. And you may ask what happens if this quant of energy is equal to the difference between 0 and second. So this is described by the second rule of choice. So transition occurs only when vibrational quantum number changes by 1, 2 or 3, and 1 for harmonic oscillator, so for ideal case, or 1, 2, 3 for anharmonic oscillator. And once again you can say, what are you talking about? Energy of oscillator, so of this our molecule, can be changed only gradually. And this tells us about this vibrational quantum number. So it means that our atom, our molecule, can absorb energy which is within the difference between 0 and first, 0 and second, 0 and third level. So our molecule cannot be transferred to some kind of 2.5 level. There are no such levels. So it can be changed only gradually. Therefore, only absorption, such absorption is allowed. So it means in Poland, dozwolone. So this absorption or oscillations are allowed between energetic levels by 1, which is called fundamental tone, or 1, 2, or 3 so-called overtones for anharmonic oscillator. So only these, let's say, transitions are allowed from the 0 to the first, called fundamental tone, or from 0 to second or to third, which are called overtones. And right now, someone can tell you got them right. And the third rule, transitions between quantum states are allowed for such oscillators whose vibrations change the dipole momentum. And once again, someone who reads this for the first time can ask what is going on. But what is the dipole momentum? The dipole momentum, or what kind of values it can take, 0 or non-zero. And it is the basis of dipole momentum are in the spatial charge distribution of the molecule. So transition between quantum states are allowed for oscillators whose vibrations change the spatial charge distribution. And here we have a physics basics as a result of interaction between electric vector of infrared radiation wave and resultant dipole momentum. From Polish, oddziaływanie pomiędzy wektorem elektrycznym fali promieniowania podczerwonego i wypadkowego momentu dipolowego. This is just the only physics, let's say, during this presentation. So, just to repeat, so the absorption of the infrared radiation may occur only when it changes or when the dipole momentum is not equal to 0. You can find such an explanation in some books. Either it is changed or either dipole momentum is not 0. But let's stick to the first explanation, that absorption may occur when the dipole momentum is changed, when the spatial charge distribution is changed as this interaction. And right now, I think everything is right and clear. So I think this was all about some theoretical basis. And right now we'll go through how the measurement looks like and what will be measuring. So we are dealing with spectrophotometric measurement. So let's consider that this grayish rectangle in the middle is our sample. On the left side we have our incident beam, on the right side we have our transmitted beam. So in our measurement we are just comparing the intensity of the incident beam and the transmitted beam through the sample. And if this beam, if this radiation, infrared radiation, goes through our material, so as we said in the beginning, either absorption or transmission may occur. And below on the left side, you see some equations for so-called transmittance and absorbance. And the terms themselves, they tell you something, they are intuitive. So absorbance, just to tell you, maybe not scientifically, but just to make it clear, how much of the radiation was absorbed, and transmittance, how much of this radiation was transmitted. And you see that the relation is logarithmic. So transmittance, it is just a ratio of transmitted beam intensity and incident beam intensity. But absorbance is a logarithm of the opposite ratio and minus logarithm of transmittance. And really important sentence, that infrared spectroscopy, so the method that you will learn how to use it, provides information about the investigated material in the form of spectrum. So the result is called spectrum, in Polish widmo, which tells us about dependence of the value describing absorption. So either it is mathematically described as an absorbance or transmittance, and it is dependence on the value describing the incident radiation. So one of these qualitative features that we told in the beginning, so energy, wavelength, frequency, or wave number. And all in this, let's say, below, in the last line, you see the units that most commonly are used for every qualitative feature. So we have a spectrum where on the y-axis we do have absorbance or transmittance. On the x-axis we have one of those qualitative features. And what is actually the spectrum? We already told dependence between absorbance and wave number in most cases. If you will look in the literature, you may find plenty times absorbance or transmittance on the y-axis. So you can use both of them. But in, let's say, 80%, people are using absorbance, and on the x-axis, in 100% cases, right now we are using wave number as a parameter. So you see an exemplary spectrum of acetone. So on the right side, you could see a formula, a structural formula of acetone. And as we said, the fundamental base is the fact that every molecule, so let's say the molecule of acetone, exhibit particular characteristic vibrations, which can be attributed to specific bonds or functional groups. And right now, if you go to the chat of Teams, I send you the link to the YouTube. You can open it right now, and you may go through, let's say it is really quick, but I highly recommend to play it with the slower speed, maybe 0.5, maybe 0.25. I will also open it on my computer, and yeah, you can go to the settings, speed, and let's say 0.25. And on this, let's say, movie, you could see these different types of movement, of oscillations, of these vibrations. So first of all, starting from the left part of the spectrum, we see that around 2008, let's say 950, we see asymmetric stretching vibration of CH2 group. So if we play it, you see that this let's say the reddish atom is oxygen, this blackish atom is carbon, and small whitish atoms are hydrogen. So please have a look that this CH2 group is vibrating, and as we said, this movement is asymmetric. If we draw an imaginable line, symmetry line through carbon and oxygen, so you see that either one or the first or second atom of hydrogen is closer to the atom of carbon. That is why we call this movement asymmetric stretching vibration. Stretching because the bond length, not the bond angle, is changing. So this is the first type of vibration of oscillation. The second one, the symmetric stretching. So the same functional group, but different type of movement. Both atoms at the same time are getting closer and getting, let's say, further from the atom of carbon. Another movement, I think the most characteristic, it is the carbon-oxygen bond oscillation. And once again, we see that the length is changing, so it is stretching vibration, but in this time we cannot say is it symmetric or asymmetric. We are just telling it is a stretching vibration of CO double bond vibration. And please have a look especially at this vibration. I will repeat once again. So one can say, wait a moment, you are telling us about CO double bond vibration, but at the same time carbon-hydrogen bond is vibrating. So what is going on here? So it is true. The person who will tell that will be true. But we are taking into account the movement which is the most intense. This is the first thing. And the second thing is that the movement of one bond influences, let's say, or has a big influence on the surrounding. So we are even telling that the vibration depends not only on the atoms, so on the masses and the bond energy, but also on the surrounding. Because CO double bond will vibrate differently in a different surrounding. If we have not CH2 group, but let's say further chain atoms or different atoms, it will vibrate slightly different. So have a look that it is vibrating differently. And fourth, so the different another type of vibration, it is a scissoring vibration of CH2 group. This time, the fifth one, we had the rocking vibration, and the last one will be wagging vibration. So these are 6 types of the vibration, and this is a really nice molecule to show you, because we see nearly all types of the normal vibrations that we were discussing. And these all we can see at the spectrum. Maybe in here you could see that these wave numbers are slightly different, but maybe it is due to the fact that this spectrum is quite old and and they are slightly different. But also it is quite important to say, to emphasize at this point, why they can be different. So you have to remember that in infrared spectroscopy we are not so exact as in like in XRD method. So we cannot tell that, let's say, alumina, like the aluminum oxide, has reflections, has pixel these signals at specific value of 2 theta angle. So in here, vibrations of specific bonds, let's say like CH2 or CO, they have so-called bands. not reflection or peaks, but bands. So we are not telling about peaky or refleksy, but we are telling about bands. So in Polish, pasma. In English vocabulary, nomenclature, you can find also peaks, but on our faculty, we are trying to teach you to recommend using only bands, just to differentiate, to separate spectroscopy from diffractive analysis. So we are telling about bands. So the signals can be found not in exact positions. Always in the literature you can find an information that, let's say, CO double bond can be found within the range of 1780 to 1740. We are giving ranges of the wave number where we can find our bonds. Why? Because our result depends on many things, on many factors, on the surroundings of the material and also of the conditions of our experiment. And where we can find such information? In the correlation tables. So the relations between functional groups and ranges of the wave number. Because some people before us, they made some calculations using so-called density functional theory. And if they put some information into the computer, into the program, into some specific software, what kind of material it is, what is the chemical formula, what type of atoms are present in the structure, the software calculated, let's say, our spectrum. So there is also a part of infrared spectroscopy when we are dealing with calculations. So how the spectrum can look like only based on our, let's say, primary knowledge. What kind of atoms are there? And if we assume if they are single bonded, double bonded, or whatsoever. And then we compare theory, so the calculations, with our experiment, And that is why we have some correlation tables in the literature. So we do know that CO double bond usually can be found, or let's say the band can be found between 1800 till 1650, depending if it is carboxyl group or carbonyl group in aldehydes, in ketones, in any other different types of material. So it depends on the surroundings. It can be found either at the higher wave numbers or lower wave numbers. And I told you something about comparison between XRD and this infrared spectroscopy, about reflections, peaks, and bands. So in here, I would like to emphasize or just explain why do we have this difference. So at the top, you see unreal case with the very sharp peaks, let's say, because these are peaks. It's nearly similar to XRD technique, but they never look like this in infrared spectroscopy. They look like on the B picture, so blurring of energy levels. Why does it happen? Why those bands, so this in Polish pasma, why they are so broad? They are so broad because of three factors. First of all, the uncertainty law of Heisenberg. So blurring of energy levels, so this is what you see on the B picture, results from the molecule lifetime. It is written in the uncertainty law of Heisenberg. Molecule has its own lifetime. The second of all, we have a Doppler effect. So blurring of this contour concerns oscillation of molecules. So you have to remember that atoms or molecules are vibrating all the time, even if we are not exposing them to any kind of radiation, even if the temperature is equal to 0. There are so-called zero vibrations. So all the time our bond, our molecule is vibrating. So that is why we have this Doppler effect. So blurring of the contour concerns molecule oscillations. And let's say third factor, so-called apparatus function. Some noises, some disturbances always occur during the measurement. And what type of values are important for us if we describe the Fourier transform infrared spectrum? So you see a typical band which can be present at a specific wave number. And here it is really interesting because I took this picture from a really nice book of Zbigniew Kęcki, Podstawy spektroskopii molekularnej, which really nicely described this method. And you see that 23 years ago, they were using not wave numbers, but they were using frequency at the x-axis. So in really old books, old publications, you can find an information that some bands are present at some frequencies, not at the wave numbers. So in here, let's focus at the first parameter, which is the most important, most relevant, most vital parameter used for qualitative analysis. I repeat, qualitative analysis, maximum position. So the wave number at which the intensity of the band is the highest. So you will be using, I think, only this parameter during preparation of the report. So we will try to describe at which wave numbers you can find some bands attributed to specific bonds. So this is, using English in the beginning, it is a little bit misleading, bands and bonds. So let's say that we have a band. So this, let's say, this is what you see at the graph, which can be assigned, which can be attributed to a specific vibration of bond. So we have a maximum position. Second of all, we have direct intensity. So simply saying just band height. Thirdly, we have integral intensity, which is a surface area below the contour. And we calculate, of course, integral of this surface area. And we have intensity, so integral intensity, which is used for quantitative analysis. Sometimes, not very often, but sometimes spectroscopists would like to say what is the percentage of a specific bond, of a specific functional group. And for example, in case of borate glasses, let's say szkła boranowe, let's say we do know that boron can be present in two types of coordination, so tetrahedral and trigonal. So in this case, spectroscopists can use integral intensity between, let's say, two bands attributed to this BO3 or BO4, so the trigonal and tetragonal boron species, and they can calculate what is the share, what is the percentage of trigonal boron and tetragonal boron species. Or let's say if someone is introducing some cations into the material, aluminum cations, silicon cations, or whatever, and he would like to know, or she would like to know, what is the percentage, how much of this, let's say aluminum oxygen bonds are present in the material, then also we can calculate such percentage or ratio between different materials. The fourth parameter, which is I think already known by you after XRD course, half bandwidth, so the contour width in the half of its height. And I think in XRD was quite crucial to calculate the dimensions of the crystals. And in here, it is more often used to describe the either crystallinity or amorphousness of the material. Because the more let's say if we have short range order, uporządkowanie bliskiego zasięgu, if we have short range order in the material, like in glasses, in amorphous materials, the bands will be broader, we say. So the half bandwidth will be larger. But if the material is purely crystalline, let's say like some nitrates or phosphates, so then we have really small half bandwidth, and then they really look alike reflections, but still this half bandwidth is larger than in case of reflections or peaks. And last information, shape of the band contour, which depends on type, distribution, and number of atoms in the investigated molecule. And please remember what I told you. The surrounding of the material really influences the let's say the vibration. So you see the type, distribution, so how atoms are distributed, what is, let's say, what is surrounding our atoms, and number, of course, of atoms in the investigated molecule. And we were telling something about changing of the dipole momentum. So the higher dipole momentum change is, the higher intensities will be. It is quite obvious, because the higher change is, we will see it as a more intense band in the spectrum. And just a few, let's say, 3-4 words about how the spectrometer is built. I really hope that you will be positive about my idea, that we will have a look at the spectrometer, because it is much more efficient, better to see it with your own eyes, and then I can show you all these parts of the spectrometer. But in here I have to describe it to you for the purpose of test and for the purpose of general knowledge. So first of all, we have to have a source of the radiation. In case of infrared radiation, it is a heated ceramic rod. And as I told you, due to the fact that we are using a range of the wavelength, it is polychromatic radiation. So we have a source. Then the source goes, let's say, goes through some specific some system, and there are plenty of mirrors, called zwierciadła, lusterka zwierciadła, plenty of those mirrors when this beam is reflected and goes to the specific position. And on the right side you also see a laser detector. So let's say it is measuring the distance that our radiation goes through the sample, and until it reaches the detector. And before it reaches sample holder, it goes through the most important part, so-called Michelson interferometer. Why it is so important? It replaced monochromator used 20 years ago, let's say, and it provides so-called Jacquinot advantage. It is just a term used in books, and plenty times there were questions concerning this advantage. But what does it say? The lack of slits limiting the beam and alignment of the beam to the possibilities of the detector. So simply saying, our radiation in the beginning is in the range of megahertz, and it is really too high frequency for detectors used nowadays. That is why this interferometer changes the frequency of this radiation to kilohertz, and the kilohertz can be easily detected by nowadays used detectors, and it provides in the end interferogram. What is interferogram? It is a relation between signal intensity. So we have this comparison of the beam transmitted through the sample and incident beam in the beginning, and time or optical path difference. So what does it mean? It means that we measure how fast our radiation went through the sample to the detector, or how was this, let's say, the optical path difference. And right now there is some problem, because we have an intensity which is okay, but we do not have any parameter describing our radiation, any qualitative feature like energy, frequency, wave number, or wavelength. And that is why this Michelson interferometer and let's say the program, the software, provides so-called Fourier transformation. That is why the full name of the technique is called Fourier transformed infrared spectroscopy, to put an emphasis on Fourier transformation. So the mathematical, let's say, formula or mathematical, not equation, but action, which changes the domain from time to frequency. Zmiana dziedziny czasu na dziedzinę częstości. So we do have a frequency, the domain of frequency. And right now we have everything, because if we have frequency, we can recalculate it for energy, wave number, or wavelength, and signal intensity is given either in absorbance or transmittance, and we have our spectrum and sample holder in between. So you see that we can have a different atmosphere. than air, atmosphere, or vacuum conditions. And in our laboratory, we have both types of spectrometer. The older one with the air, when we can see the influence of carbon dioxide or let's say water present in the air, or the vacuum conditions when we have no influence of such species. And it is important to remember that water is a really messy messy molecule in case of infrared spectroscopy, because sometimes scientists would like to know something about percentage, the share of hydroxyl group, let's say aluminum, oxygen, hydrogen, silicon, oxygen, hydrogen, about some hydroxyl groups, or the percentage, the share of water in the material. And we have to remember that water is present in our ventilated air, in the classroom, in the laboratory, and also water can be present in the material itself. It can be wet. So that is why I will, let's say, always trying to tell you that the sample, in the best case, is completely dry. And we can have two types of instruments, single beam or double beam. What does it mean? Double beam, it means when we have two sample holders, one will be for a reference, the second one will be for the material. And with the single beam instrument, we have to make, first of all, the reference measurement, and second of all, our measurement with the reference material. What does it mean, let's say, reference? I will go, right here. So the most common used technique, transmission pellet technique. You could see on the pictures on the left side the mortar with sample which is grinded, which is fragmented. In the middle you could see the press, the oil press that we are using also in the laboratory to prepare so-called pellet, in Polish pastylka. And on the right side you could see a metal holder for this pellet, which is, let's say, visible in the middle as this bluish, let's say, as this bluish sample. It has dimensions of 1.5 centimeters in diameter and around 2-3 millimeters in thickness. And such pellet, it would be too much of the substance for the measurement. That is why we have to use some material, some reference material, which will act as a matrix. So we are using KBr, so we are using potassium bromide. So we are mixing, as you can see at the first point, we are fragmentating 2 milligrams of the substance. Why it has to be fragmented? Because crystal dimensions have to be smaller than 2.5 microns, which is the lowest possible wavelength used in middle infrared spectroscopy, in order to avoid signal disturbances. Because if these grains will be much larger or in the range of infrared radiation, we can have some reflection or scattering of the radiation on these two big grains. That is why we are fragmentating it, so it has to be well grinded in the mortar, and then we are adding 400 milligrams of potassium bromide as a reference material. And why? First of all, it is plastic. It can be easily pressed with the oil press to form such a pellet. Secondly, it is totally permeable in the middle infrared range, so there is no absorption and total transmission. We are even saying in Polish that KBR jest spektroskopowo przeźroczysty. So it means that no middle infrared radiation will be absorbed by KBR. So it will be only absorbed by our investigated substance, and KBR will be totally permeable. It only acts as a matrix. And what about KBR? The material itself, so the substance, the measured substance, can be grinded, well grinded, to have fragmentation below 2.5 microns. But KBR is highly hygroscopic. That is why after classes, after measurements, it is stored in desiccators, well closed, but also it should be mixed with the material, not grinded, because we can put some water from the air into the material and then our measurement will be falsified. And the last information, when do we know that our measurement is correct? And why I told you that the pellet cannot be made out of the material itself? Because signal only is taken only from the tested substance, and we see that it is efficient, it is correct when the level of absorbance is in the range between 0.4 to 2, and in the best case it is around 1. If we will make the pellet from the investigated substance, we will, let's say, use plenty of substance, and we will get too high absorbance. So in your case, in the laboratory, let's say sometimes students have to repeat the preparation of pellet, which takes around 1 or 2 minutes, because in the end they get a result, so the spectrum and the level of absorbance either below 0.4, so it means they have to put more substance for the preparation of the next pellet, or it is higher than 2, so it means they have to repeat the preparation using smaller amount of the material. And we omit one slide. What kind of techniques do we use? Transmission we already discussed. So our beam is transmitted through a pellet when we used a KBR as a matrix. And it is the most important, the most common. In 90%, 95% cases, it is used for this method. The two other, which are used or 2 or 3 other, which are possible in our laboratory, and I would love to show you them. And if someone of you chose, let's say, some coatings for our classes, it will be also possible to measure using reflection absorption technique. When our material, you see it on the left bottom side, the reflection absorption, when our beam is just reflected from our surface. And basically the most of the coatings which we are measuring, they are deposited on some metals, and metals are not absorbing infrared radiation. That is why they are reflecting it. So the only part which is absorbing is this thin coating material. On the right side you see attenuated total reflection, so-called ATR. So this is a technique, so in Polish called technika wewnętrznego odbicia, całkowitego wewnętrznego odbicia, which is used for fluids. We can also measure fluids, some liquids in our laboratory, but unfortunately we cannot measure it with SEM. And on the right side, diffuse reflection, which is the only case, let's say, in which we are not only dealing with absorption, but also with some, let's say, diffused radiation. And 2 other techniques, which are emission and photoacoustic, which are used really, really rarely in the literature, and we will not discuss them more in detail. All right, so in the end, applications of near infrared, far infrared, and of course our middle infrared spectroscopy. So near infrared, bliska podczerwi, so the humidity, let's say, in flour, starch, chips, the analysis of reflected light spectrum, or the one reflected by the planets, or the one which is not written here, plenty of ionic materials. I told you something, and I think it will be wise to go back in here to KBR. I guess that you, let's say, for sure you know what kind of bonds do we have in our materials, like ionic, covalent, van der Waals, metallic, or mixed ionic covalent. And I already told you we can measure solids in the form of bulk, powder, coatings. We can measure liquids. There are also special attachments for gases, but we do not have it. We do not have one in our laboratory. But also, what type of bonds we can measure, it is important. We can measure usually either ionic covalent or ionic bonds using infrared spectroscopy. But most of the material which are measured in middle infrared, are mixed ionic covalent, and purely ionic materials as KBr can be measured in near infrared. So that is why potassium bromide can be well used as a matrix for middle infrared spectroscopy, but because there is no absorption. But if we use it, let's say for near infrared, there will be a huge, let's say there will be a beautiful spectrum because it is a purely ionic material. And in case of middle infrared, there are only, let's say, we can measure them, but the bands which are present, they are really not intense. That is why in our laboratory we have also attachment for near infrared region. Okay, and far infrared, let's say the investigation of the resonance of crystal structure and evaluation of the amorphousness of the material. But the most important is middle infrared spectroscopy. So first of all, identification of crystalline structure, most often used as a complementary method to XRD. Second of all, as I already told you, evaluation of short-range order character in amorphous materials, glassy or amorphous materials, in plenty of silicate glasses, borates glasses, or phosphate glasses. And this is how much time do we have? It's already okay. I think it's one of the last slides. So short range order, and it is really important to see the difference between short range order and long range order. Long range order you were evaluating using XRD technique method, and in this case all of these glassy materials, all amorphous materials which cannot be measured using XRD can be very efficiently measured by infrared spectroscopy. Then determination of molecule structure by means of group frequencies tables. So we are using these correlation tables. Evaluation of compounds purity. So if we have spectrum recorded in ideal conditions of some pure material, and then we would like to see if our material wasn't contaminated, then we can compare both spectra. Why it is so important? Because this technique is very, very sensitive. You saw that we need around 2 milligrams of the material. So if we have any dust, if our mortar is contaminated with some substance after some measurement, we have to really clean it with acetone, and we have to wear gloves. We have to be really careful because it's so sensitive that any kind of dust, any kind of grain, small grain or dust will falsify our measurement. Controlling the reaction flow, the quantitative analysis as I described you. So what is the share, what is the percentage of a specific molecules, and investigation of intramolecular interaction. And apart from that, this theoretical calculations. So someone, let's say, is trying to find a new compound, trying to synthesize new compound, and then first of all he can calculate the theoretical structure. Afterwards, he synthesizes or she synthesizes in the laboratory and makes such an experiment, and we can compare theory with practice with our experiment. Yes, important. And here is just a quick example from my own work. When you see some spectra on the bottom and on the top, the reddish and the greenish at the top, and the process of so-called deconvolution. What is deconvolution? In Poland, rozkład widma na pasma składowe. Because in some points, if you have a glassy material, please have a look at this spectra, this red and the green at the top. They are really broad, and you see that bands, you could distinguish maybe 3-4 bands, and please have a look how many bands are, let's say, hidden below this complicated contour, like nearly 15 or 16. Why? Because software and this, let's say, program and the technique is not somehow able to distinguish all these bands, because we are telling they are overlapping, nakładanie, overlapping of bands. They are too close to each other to be well distinguished. The only what you can see is that there are some kind of bumps on the contour, so-called przegięcia, that if you, let's say, look at the 1200 at this wave number, you see that there is not such a clear band, but there is some kind of bump at the contour. So it tells us that something is hidden there, but it is too close to another band. That is why we cannot see it in this complicated contour called in Polish obwiednia pasma. Okay, and what does it tell us? It can tell us about the presence of some bands in the material. And let's say in the upper one, I was trying to, let's say, introduce aluminum cations into the material. And I found two additional bands in the structure, which come from silicon, oxygen, aluminum linkages, not present in the pure material below. So then I can confirm that I introduced some, let's say, aluminum in the form of such bonds into the material. It is just one simple example for qualitative analysis. And if you please can you still hear me?
Yes.
Okay, perfect. So sorry for making it too long. Just, it is the last slide. The comparison between infrared spectroscopy and Raman spectroscopy. For those who are more interested in Raman, and it's, let's say, you are using it, you want to know more, we can discuss it either after classes when they take lockdown, or you may take part in additional classes with Professor Włodzimierz Mozgawa at our Department of Macromolecular Compounds and Chemistry of Silicates. So this, he is running classes, I think it is called Advanced Methods of Research Investigation, like zaawansowane metody badania materiałów. And then you will have classes with Dr. Piotr Jeleń, who is really experienced in Raman. And as far as I know, then he also gives you a chance to prepare any kind of substances, and then you are measuring with Raman spectroscopy and get more information about it. But what are the differences, the most important differences? Rules of choice. In infrared spectroscopy, as you remember, we are dealing with atomic cores, with the movement of atomic cores. So we are interested in the change of dipole momentum, of the spatial charge distribution. In case of Raman, it isn't, let's say, we are not caring about dipole momentum. We are caring about valence electrons. So we want to have a change of polarizability. Second thing, the physical phenomenon on which our techniques are based. Absorption in case of infrared radiation, of infrared technique. In case of Raman, it is scattering. So absorption and spontaneous emission. And this is what we measure in the Raman. We measure the difference between incident beam intensity and this emitted beam intensity. And measured range. So in infrared, we had, as the name says itself, in the infrared range, in case of Raman, visible light and near infrared, and the source. In case of infrared, we had this, we have heated ceramic rod, we had the polychromatic radiation. In case of Raman, we have a monochromatic radiation because our source is laser light. And I think here you can find some literature. I recommend the book of Zbigniew Kęcki for those who want to get deeper into this topic. I think this was everything for today. So I would like you, in the end, to maybe I will just quickly check how is. Okay, I see that Miss Zuzanna Kantor didn't signed herself in UPEL. Is it correct? Do you have any problems with internet?
Yeah, no, I just didn't know I was supposed to do that, and I will just do it right now. Okay,
perfect. I hope that you can still do it, because it's already after the time of classes. If not...
Excuse me, can I have the question about your presentation?
Absolutely.
You plan to share it with us or not?
You mean the presentation?
Yes.
Yes, I will send you some copy. I will send you some copy, maybe to Mr. Patrick Zions. I will send him the copy. I would say without question marks, because you were obliged to pay attention during the lecture, and without GIFs, because I don't want to share with you some material from the internet.
Okay,
so I will do that. And what I want from you is feedback, maybe from Mr. Patrick Zions, who will send me this table with division for subgroups of 2 people or 3 people in some case, with your substances, and then I will give you feedback if these substances can be measured. So please remember, what is it, in what type of form, powder, coating, or bulk, and the last thing is that you will somehow decide about those laboratory classes. As I repeat, I highly recommend that. I'm telling you, I'm really flexible. It is just for you, not for me. It is just for you to be in the classroom, in the laboratory, to get to know this technique well, to feel what is going on, to use the proper software, which is used usually by us, and to have a chance to sit in front of microscope, to take pictures by yourself, to measure the elemental composition. And I think that's all for today. If you have any questions, please do not hesitate. You can always write an email afterwards. Do we have any classes right now?
In half an hour.
In half an hour, okay. So if any one of you have some questions, please ask.
I have one considering the attendance.
Okay.
So turns out I think I cannot log in right now.
Okay, it's not a problem. I will take this list, but I will also take the list from the Microsoft Teams. So you were all present, so there is not a problem.
Okay, sorry about that. I didn't know
No,
I was supposed to do that.
It's okay. Okay, so if there are no further questions, so thank you very much for today. I hope everything was clear. And yeah, I'm just waiting for your feedback. I want to wish you happy Easter, all the best for you, and write me an emails whenever you want, whatever you would like to discuss. And that's all for today, folks. Thank you very much. And goodbye.
Thank you.
Happy Easter.
Goodbye.
Bye.